Professor Yiran Chen received BS 1998 and MS 2001 from Tsinghua University and the PhD 2005 from Purdue University. After 5 years in industry, he joined the University of Pittsburgh in 2010 as assistant professor and then promoted associate professor with tenure on 2014. Holding B. Centennial Alumni Faculty Fellow. He is now professor of the Department of Electrical and Computer Engineering at Duke University and serving as director of the NSF AI Institute for Edge Computing, leveraging the next generation network, Athena, and the NSF Industry University Cooperative Research Center for Alternative, Sustainable, and Intelligent Computing, and the co-director of Duke Center for Computational Evolutional Intelligence. So, has published one book, 500 technical publications, 96 US granted patents, associate director, associate editor at various periodicals, and serving as technical and organization committee. Is serving as editor-in-chief in the IEEE Circuit and System magazine. Received 8 Best Paper Award, 1 Best Poster Award, and 14 Best Paper nomination from a reputable international conference. I'm sorry, I'm just jumping on your CV, which is impressive, and received numerous awards for his technical contribution, such as the IEEE Computer Society Edward McCluskey Technical Achievement Award, ECM SIGDA Service Award, and is a fellow of the SCM and IEEE, and now serve as chair of ICM SIGDA. Hope I represented correctly, Professor Chen. I leave to you the floor. Thank you.
Okay, Danilo, thank you so much for the introduction. Yeah, I will be very happy to give a talk here and about federated learning, which is a little bit different from what Song and also Hiroki gave just now. Talk about training and also the inference on the edge. We rather to move our focus to more system level. Okay, let me see. Yeah. We're basically going to report 3 topics. The first 2 are about the efficient and also heterogeneity-aware federated learning, which were published last year in ICEC and Census. So there is one more topic we want to discuss regarding the privacy enhancement in the federated learning too, which was published in the 3PR last year. So now let's look at the first topic, which is called the lottery federated learning, or LotteryFL, talking about how we're able to improve the edge intelligence with the personalization and also communication efficient federated learning. So people may be very familiar with federated learning in the tinyML setting, because after you have very tiny edge devices, you need to figure out a way to connect them together. So, and not just connected, those devices, but also we need to make sure all the devices are contributing to all the training data of the system to make sure we can maximize the use of every single device. So federated learning was proposed, for this purpose. For example, all the edge device we'll call clamps, will be able to contribute to the data to the centralized server, we show here. So we're able to train our model in the server and deploy the model back to the different clamps. And in many cases, we have to do some customization in the local edge device to make sure we can adapt to the local requirements. And federated learnings can be used for many applications, such as the online banking, some security, or some product computing, or so on first. We show here. So if you look at the challenges in the federated learning, there are at least the 2 challenges here. The first one is the communication efficiency. The reason is after we train the models on the edge, we have to send many data, or at least the features of the data, to the centralized server. So the total communication cost will be the product of the communication runs times by the number of the parameters we transfer in each run, and also the average code word length of each parameters. Let me give one example. Let's say we try to train the VGG16 on the image night using the federated learning, and the number of the runs until convergence will be the 9,000. And the number of the parameters, on this network will be something like 138 million. And then the bits per parameters, because we can transfer the gradients, to the centralized server with the source 32. And after we converge the model during the training, the total communication cost will be close to, 500 terabytes. Certainly, that's going to impose a larger burden on the communication, and more than that. So we need to handle the statistical heterogeneity on the different devices, especially, the data on each device are highly non-identically distributed. Basically means that they follow the different distributions. And the global model learning using the Fed average was a very naive federal learning framework, does not perform very well if such a data heterogeneity is considered. One example is here saying, if we are training the CFAR10 on this federated learning framework, if the data is IID, which means identically distributed, the accuracy will be like 89%, 90%. But if we consider the real or the practical setup with a non-IID, then the accuracy will drop below 50%. So the motivation of LotteryFL learning when we propose is trying to improve the communication efficiency and achieve the personalization under the non-IID setting. Here, the personalization means we need to fine-tune the local network or customize the local network to adapt to the different requirements on the different clients. So that's a non-IID plus a personalization will motivate us to seek for the device-specific lottery ticket subnet. We call the LTN for each device, and we show here. And here, the lottery ticket means we already have very large network, which is shared by all the clients, but we only have the subnet, on each device, which can perform the task on each client. So by doing so, we don't need to send all the parameters of the singles, the shared model to the centralized server. Rather than we only send the gradients or the parameters associated with the subnet, to the server. So that's going to dramatically reduce the communication cost between the centralized server and also the clients. And of course, they're going to reduce the computational cost on each client because we only need to calculate a portion of the original networks. And this customized subnet will be different from the device to device and to adapt to the different needs. So now the question will become how we're able to train this local lottery ticket network or LTN in the local, and how we are able to do the aggregation between the different lottery ticket networks sent from the clients. So we're going to download the subnet from the server. And here we understand for each client we'll have a different subnet. And we're going to prune and recite this subnet if the accuracy is larger or higher than some threshold. And if yes, actually we will continue prune the neural network to make sure the accuracy will just barely meet the target. So in Song's work, he has given many examples about how we're going to do the pruning, quantization on those network. It's be very similar. Actually, our method can take whatever people develop to do this work. We're going to perform the training using the local data and then update the parameters of this subnet, and then send them to the global server for the aggregation. So why we want to do the aggregation? Because we want to make sure we take into account the contributions of all the clients, so that we can take advantage of this varieties of the data. So the intuition here is we're going to consider this non-IID distribution across all the columns, and only need to, and by assuming this LTN of each column, will not significantly overlap between each other, so that we can constrain the aggregation computation within the very minimal overlapped, the parameters. And we're going to perform the aggregation on only this overlapped element, among all this LTN, while keep the rest of the non-overlapped element unchanged, because this element basically represent, the personalization requirement of each class. So we actually do some evaluation on this non-IID setting by limiting the training data to only 10 to 40 samples on each device, because the assumption here is device may not have enough sample to train the models. That's why we need the federated learning to have the contribution from all the columns. We also have a statistical heterogeneity requirement, so that we only have 2 classes of the samples on each device, so that no device will have all the classes with sufficient samples. That's another reason we need all the columns. So the data will be very unbalanced, which means the one class may have many data, another one have only a fewer number of the data. That's also very common if we see the heterogeneity on these columns. So the baseline will be start along, which means we'll train our model in the local. Then we're not going to enjoy the contribution from different columns. And we have a fed average. That's a very naive, the federated learning framework, and also the LG federated learning, which consider the global model training with the local fine-tuning. We'll evaluate both inference accuracy and also communication cost, and see how we are able to trade off them. So so we have very limited data volume, and we just mentioned it. We have only 5 examples per class, or 10 examples per class, or 20 examples per class with balanced data. So we will find out that the lottery federated learning will improve the accuracy by 13 to 15% compared with LG federated average. That's the state-of-art baseline. And the communication cost reduced by 34 to more than 50%. And so the reduction of the communication cost came from the reduction of the parameters we need to transfer between the clients and also the global server. And the interesting part is, if we have the more examples in the local, they're actually going to improve the convergence, the speed of the global training model. That's going to reduce the number of the rounds we need to send between the client and also the server. So the total communication cost will reduce further. So that actually means there is trade-off between the sufficiency of the data in the local and also the collaboration between different clients. And also if you have unbalanced data, which means we have one class has many examples, another class has very fewer number of the examples, then we see the continuous increase the accuracy using the lottery federated learning with the increased communication cost. And we want to show here, because the unbalanced data basically means we need more rounds or more time to converge the training the model. So that is something we learned from this research. So after we finish this work, we actually try to see if we can do even more aggressively, because we understand we still need to create the original model, and the model actually needs to be transferred from the client to the server, and we need to transfer floating point value from the client to the server. Can we do more than this? So we came up with something we call FedMask. Okay, so FedMask is a technique which we have, the large original model, but rather than we have a subset of the model, we actually create a mask on top of this original model. So mask is the has all the binary now elements 0 and 1. So if we have a 0, then we're not going to allow this parameters to transfer between the local model to the server. I should not even use this parameter to process the local data. But if the element is 1, then that will be retained and participate in the computation. The hypothesis here is we have a larger number of the probability to create the different combinations of the mask element that may be sufficiently large, so that we can adapt to the requirement of the personalization on the clumps. If we have the well-initialized, original neural network and train it very well. And why we want to do this? Because if we have such a mask, we're able to, adapt to the need for the local clumps. We only need to expose, the filter out, the parameters, to the server, and we don't even need to transfer the parameters. We only need to transfer the mask to the global server and do the aggregation on top of this. And by doing so, we actually will dramatically reduce the computation cost because we only send 0 and 1. And we'll still be able to support the personalization and also the communication cost and also computational cost and also the memory usage in the local because we only need to store the mask. Okay, now let's look at how we can design this. We learn a heterogeneous and structural sparse binary mask. It's very similar as we train the neural network, but we apply the structural sparsity on this binary mask so that we have a highly optimized mask to guide the generation of the final neural network running on each clumps. So we only communicate the binary mask, which is 0 and 1. And the binary mask will be element-wise applied to the frozen parameters to generate the personalized and structural sparse model as a local, basically on the clump, to execute the application on the clumps. So now my question becomes why we want to do this? Because if we apply the structural specification on the binary mask, we can get rid of, for example, the whole channels or the whole layers, such and such. And by doing so, will be perfectly support the very limited computational cost. Some very limited computational resources on this edge device like MC or so on first. And also that can reduce the memory usage. And there are tons of ways, we're able to apply the structural pruning or also quantization on the binary mask. So I don't need to go through all the details. So another question we need to consider is actually the aggregation of this mask, because when we are sending the mask to the global server, we want to make sure we'll take advantage of the contribution from all the clumps that require us to aggregate, this mask element. So what we're doing here is, if we see the overlap between the two masks corresponding to the same channels from the different devices, then we're gonna do the aggregation in element-wise. For them to have a 0 and 1, we know, if we do the centralized the aggregation, we have a 0 there. But if we totally remove, the mask corresponding to one channel, then we're not going. We will untouch another mask and still, inherit this mask, to our aggregated result. One example you can see here is that we have a yellow one and a blue one. And both of them corresponds to the channel 1 for the device I and J. So we do the aggregation and generate the green one, which is aggregated mask. But if we have the channel 3, so one has the mask, one does not have the mask, then we're not going to touch the yellow one. So this one will keep the same and pass to the aggregated output. That's how we do the aggregation. So we actually test out our result on the real, test bed we designed it at Duke. So we have different devices connected through the different ways. For them, we have NVIDIA GPUs and embedded GPUs, and also the Raspberry Pi, the cell phone, the laptop, and they are connected through the Ethernet, the Wi-Fi or some first, so to mimic the different environment on the connectivity and also the computational resources. And the result on some of the results are presented here. We have a EM NIST, well, CFAR10, HAR, and Shakespeare. So with multiple baseline, some long Fed average, top K, or some first. I want to pay attention to the BAN Fed average, which is using the binary neural net plus the Fed average, because they also send the binary information between the client and the server that could be generating the comparable communication cost. However, look at our result, which is the right star called the FedMask. Our goal is trying to achieve the accuracy, inference accuracy with access is as high as we can, with the lowest communication cost or communication time. So the right stars show on the right and the bottom corner. So if you look at the BAN Fed average, the communication cost is also very low, but the accuracy is really bad. So which means the binary neural network is not be able to support in this particular case, especially for the large data heterogeneity. And for some other method, they may achieve a similar accuracy, but with much larger communication time, or other, cost. So if you look at the runtime performance in terms of the memory footprint and also the inference, the speed and also the energy. So the FedMask model, which on the left column has a smaller memory footprint compared with the baseline model. It's actually much larger than the binary neural network, because we still do keep, the floating point original network with the mask. But this will be significant smaller than other baseline model. If you look at the inference speed up, we actually dramatically improve the performance by about 1.4, 1.5 times. Binary neural networks sometimes give us the more speed up, but with a much lower accuracy, and a similar energy saving can be achieved compared with the regional our baseline. So that is our concurrent here. So the last topic I want to talk about today is a sortiera. That's basically the defense, against the privacy leakage in the federated learning. I know today we have been talking a lot about the efficiency or accuracy, but I want to move our focuses, from the computational metrics, to the security metrics. So the issue here is, in federated learning, the data representation may be leaked. So through the information we exchange between the client and also the server, the gradients is one example. This such a leakage will allow us to explicitly reconstruct the input data utilizing the representation of each class on the device, from the gradients. One example is here, say if we have a ground truth, which is on the left column. If we have the whole gradients that can be exposed, to the adversarial, then we're able to restore, those information. But if we only, have the convolutional layer gradients, then that won't carry enough information. We don't worry about that much. But if you have, the data representation on our gradients, you will be able to see we're able to recover from those information. So in the practical federated learning applications, the number of the batches and the local training epochs of each device are both small because of the small number of the training data at local servers. So reduce the data representation entanglement further and make us easier to reconstruct the original data. The image is just one example here. So the representation, such representation attack can be defended using the perturbation on the input. So if we want to achieve this goal, we need to basically satisfy two goals, simultaneously. The first one is reducing the privacy information leakage, which means the reconstructed input are taken, through the perturbated data representations, and the raw input actually should be dissimilar. well, to maintain the original federated learning performance, then the perturbed data representation R take and also the true data representation the R without the perturbation should be similar, right? So they basically become the min-max skin and can use the manual constructive learning, to optimize both skins simultaneously, and we list it here. So we actually can rewrite this formulation to another format, which I show here. So we try to satisfy that we can reduce the dissimilarity within some threshold. We want to maximize the similarity. So here, we can have a different method to quantify the similarity and the dissimilarity, using P and Q. And we set a P equal to 2 to maximize MSE between the reconstructed input, because we're using the image, as one example, and the raw input. And meanwhile, we set Q due to the two reasons, because our defense has an analytical solution, that's number one. And number two, we basically count how many parameters we're going to transfer, between the clients and also the server, and perturb them. And the smaller number means the lower cost. So Q basically just count how many number we need to change. So we will have a certified, the robustness guarantee, and also here, I'm not going to all the details because you can read our paper. So basically, we can guarantee that the dissimilarity will be larger than, some threshold which, set by the similarity between the feature we're trying to extract from the federated learning, and also some derivative of the transfer function. So the evaluation is quite simple. We try to make sure we have a minimal impact on the model accuracy with a maximized MSE between the reconstructed output and also the original output. So we have a data side, like non-IID CFR10 and also non-IID MNIST. And we have two attack methods, including DLG attack and also gradient similarity or GS attack. There are two defense baseline, the gradient compression and the differential privacy. And you can find out that is a black line show that our method can maintain very good model accuracy with much larger MSE we can achieve, which means we can maintain the original performance very well, but still have the larger dissimilarity we can achieve between the reconstructed value and what we want to preserve. So, okay, to recap today, this talk, which I picked the three topics, regarding the efficiency and also the privacy. Originally, we have the lottery ticket. We just send the subnet of the neural network between the client and also the server to make sure we can improve the communication efficiency with the personalization. And for the FedMask, we actually further improve this by reducing the computational cost on the edge device, or the tinyML device with a smaller requirement on the memory, while still maintaining the good communication efficiency and also the personalization. And then we realized, the gradients we exchange between the client and also the server will leak the information of the original data. So we try to perturb, the data a little bit so that, people become harder, for the people to reconstruct the original data and improve the privacy of the original data. I will stop here and try to answer any questions there. Yeah. Thank you.
Thanks a lot, Professor Chen, for your great talk. As before, there are questions in the chat. We will try to go through some of them, and for the others unanswered, please kindly find some time to type answer. So let's start from the first. How the on-device training is performed in resource-constrained edge devices, low tiny memory and compute and energy, the LG Fed average method?
So it's a very good question. In the LG Fed learning, they actually try to fine-tune only a few layers of the neural network or something first, to minimize the training cost. They never try to train from the scratch, or they use a limited number of the training data to train. Yeah, that's a very common practice. Yeah.
Thank you. Second one, in terms of gains in communication efficiency, scalability, and heterogeneity, max number of supported clients, and adapting to resource and data needs for heterogeneous clients, formal privacy guarantees, for example, secure aggregation, real hardware support, for example, MCU, CPU, GPU, and federated learning strategy, for example, FedMask, FedAgregation, FedProx, FedAdagrad, etc. Where does your framework stand against other frameworks such as Flower, IBM, FL, OpenFL, TFF, FATE? And another question is, what an on-device learning technique do you use during local client training?
Yeah, that's a very good question. We're not trying to develop another new, federated learning framework, to against the existing one, rather than we are designing the methodology which can be implemented using those framework. Yeah, so for the on-trip learning technique we use during the local client training, I think we don't develop any new stuff. We just use whatever we can find out, because there are tons of research already there. We just find out the best one which can adapt to our requirements, such as structural pruning. That is the what we need, because we want to make sure we have a structural pruning to characters which can easily the aggregation on the server. So we don't design anything new. Yeah.
Thank you. I think this you already answered. Perhaps what is the initialization of the model parameters? It is randomly. Is it a randomly initialization or pre-trained? I think you said there is a
that really depends on which technique we use. There's some technique like binary neural network. I believe the original paper is just randomly initialized. But there are some other papers they actually going to pre-train the model. Then they use very the NAS design, the one for all, to pick only the portion of the neural network, for the different personalization. But there is no such constraints or the fixed solution there. Yeah.
Okay, thank you. Next, I noticed that most of the datasets used for evaluation in federated learning are image-based datasets. Do the proposed methods also work for time series data? Are there any time series datasets that are suitable for benchmarking federated learning?
Yeah, it's a very good question, actually. Yes, I think you're right. Many federal learning work based on the image. There are some work, talking about the NLP-based federal learning framework, also some benchmark there. So, but compared with the image, it's much, it's not that popular. But there are some work and talk about the NLP-based federal learning. Yeah.
Thank you. And the last question, how do you make sure that a large number of adversary devices don't skew the global model by sending local model parameters for federated averaging?
Yeah, it's actually a very good question. There are some papers talk about, the poisoning attack on the federated learning. Even us had one paper I did not include because of the time limit. It's a federated learning, it's an FLWBC, the white blood cell. So because if we have a large number of the adversarial devices, if they give us the wrong labels, it's not just attack the current round. There is something called the long-lasting effect going to affect the following round, then until the whole system recover. So to defend this, you need to add the perturbation on some data to make sure you will fill up the Hansen matrix, and also minimize we call the long-lasting effect. So you can read our paper for more details. It's IFL-WBC, which was published, I believe, last year in NIPS. Yeah, NEURIPS. Yeah.
Great. Thanks so much, Professor Chen. There is another question, but you know, we are running out of time, so I kindly ask you to reply, to type in the answer. Thanks a lot for your time, for your availability. Great presentation. Thanks the strategic partners once again, because without them, these type of forum and many other initiatives would be impossible to organize. And the strategic partners are ARM, very quickly, Edge Impulse, Qualcomm. Then we have the Platinum strategic partner, DeepLight, Clicatech, Reality AI, Renesas, Sony Semiconductor, the Gold strategic partner, Analog Devices, PhotoHub, Microsoft, NXP, Seed Studio, SensiMil, STMicro, Synaptics, ScienceSense, and then a bunch of silver strategic partners, which are listed here. Thanks a lot. It was really a great afternoon for me and whatever is your time zone. Thanks a lot. No words to express gratitude to the professors and all to attendees for being patient for the extra time. Thank you and see you tomorrow. Have a nice day or evening. Bye.